All right, everyone, welcome to day 2 of the Intro to Data Science with Python workshop. We're all logged in. We're kind of ready to go. We've gone to the GitHub page here that's been set up for this workshop. Again, it has all the notebooks, all the material, all the data that you'll need for this workshop, and yesterday's workshops are here. If you come to this page, launch Jupyter Hub with this link if you're UCLA affiliated. If not, you can use the binder. Once you're logged in, you get to this page here with a list of all the notebooks within your Jupyter Hub environment in the classic notebook. You can go back and run Ben's workshops from yesterday's by just clicking on this and going through the motions of running this. Just another note about the recording. This is obviously being recorded. We will make the 2 workshops recordings available on our IDRI YouTube channel. If you are registered, you will get an email in the next few days with a link to the recordings. So for the most part, it is a hands-on workshop, but if you get lost, don't feel like you have to try to catch up. Be comforted by the fact that it's being recorded. Sometimes it's better just to sit back and enjoy the show and not be panicked in trying to catching up with what we're doing. And again, feel comforted that there is a recording that you can go back to and run through the steps. All right, so I'm going to get us started. Number 4, Socrata MapRS notebook. Go ahead and click on that. You should get to a page that looks like this. I'm going to go through this notebook in presentation mode. I don't recommend that you go through it in presentation mode. I recommend that you go through it by scrolling down, highlighting a cell, and remember Shift-Enter is the kind of magic execution code for the cell that takes you and executes the cell and takes you to the next cell. Shift and Enter. But I'm going to go in presentation mode. I use a plugin called Rise that allows me to go into presentation mode. So my screen might look a little different from yours, but it's exactly the same content. So I'm going to go ahead and start us here. So yesterday, we covered kind of the fundamentals of Python and data science, I should say. And today we're going to kind of go into a little more sexy stuff, kind of more fun stuff in terms of, so part 1 of today is a real case study and part 2 is machine learning. These are 2 really great topics to cover for our second day. The fundamentals was maybe kind of have to slog through it a little bit. You know, I coach soccer and basketball, so these are kind of like the boring fundamental drills that you have to learn in order to play a game. And when you play a game, you start to understand, oh, that's why I had to learn the fundamentals. So you guys all survived day 1. So now we're ready to apply some of that stuff in a real kind of life scenario. All right. So what I like to cover today, I'm a social scientist, an urban planner by trade. So something that's a little closer to home for me. It may not be for some of you, but I think it'll be a fun project inquiry for any of us because it's relevant to our day-to-day life. So I'm going to look at crime hotspots in LA over time. And just looking at this title, Crime Hotspots in LA over time, is very indicative of a lot of things that we're going to cover today. So what are we covering? Crime. So this indicates the data that we're going to be using. We're going to look at some kind of police data, maybe, arrests that comes from the LAPD. The word hotspots, what does that refer to? Or what does that indicate? That actually has a locational element to it. We're looking at clusterings of spots over space. So we're trying to identify hotspots when we map crime over a wide area. LA is obviously the focus, the spatial focus that we're looking at. And then finally, the term over time is also an indication that this question is going to cover longitudinal data. So we're not only looking at something that happens once, we're looking at something that happens over time. So there's so much to unpack here, and let's go ahead with it. All right. So the first part of a data science project is, like the word indicates, data science is data. So we can't have a data science project without data. And data acquisition is step one. And it will dictate a lot of what happens next. So for this inquiry, I'm going to use a platform called Socrata. Socrata is a US-based kind of governmental platform for data, for open data. So when you go to the Socrata website, it's built by Tyler Tech, which is a private company. And they've built a platform called Socrata that has been championed by governments, municipal, federal, local governments all over the United States. And it's a platform that allows you to, for transparency of data in this kind of world of the digital city. The transparency of information has become something that's paramount for local governments to inform citizens about what's going on in the city. And they've championed this platform called Socrata. So the part that's kind of maybe relevant for us here, open data and citizen engagement. This really empowers us as citizens to get data that's being provided to us by the police department, by building and safety, active businesses, things like that, so that we can run our own inquiries about what's happening in our spaces and around us. And then insights, to learn about our city spaces through this information. Some of the examples of municipalities that use Socrata, I have 4 here. So we have San Francisco. San Francisco has kind of been a big pioneer early on about open data. So they have a robust portal here that uses Socrata. We have Chicago here as well, LA, which we'll get to, New York. Shout out to those of you who are in the East Coast, and I know there's at least 2 of you here from New York. New York has an awesome data portal. Again, it's like a search engine for their data. All this data is made available by the different departments within the government in New York. I like their website. It's very kind of user-friendly, easy to use. If you're new to open data, there's resources for that, what data is and so forth. And they have projects by people like us who can post projects that utilize their open data. So if you look at some of their projects, it's really cool because you can learn how regular people, academics, community activists have utilized this data for maybe some kind of social justice issue. And these all are available. It's live. Here's one from a college student who created a map using the data that's provided here. And you can actually launch the project and have a look at what this person did, the source code. And this student actually put together all his data, everything in a Jupyter notebook. So you can now kind of start to understand how Jupyter notebooks can empower you to become a data science, provide a workflow, and provide results that can inform policy and move an agenda forward. And this is an interactive map, color-coded points of educational institutes in New York, all in a single Jupyter notebook. So we're going to do something similar today with data from our very own LA data portal. Okay. Any questions so far? Were we doing good? All right. All right, so for this tutorial, we're going to look at LAPD's arrest data. If you take a look at this data, I'm going to click on that link. It's going to take us directly to the LA data portal. I've already pre-selected a data set for us. But you can, you know, with a search button here, you can search for, they have thousands of data sets, so you can search for different data sets. Some of them have locational attributes, some of them don't. I'm a cartographer by trade as well, so I love mapping information, so I'm always interested in data that can be mapped. I picked this particular data set not only because I have done a lot of crime research myself, but because it has, if you look down here at all the fields provided here in this data set, there are like cross streets, address, latitude, and longitude coordinates. So when I see this, I instantly know that we can create rich visualizations of this information because we can create maps. So this has the attributes that I'm looking for in data, which is time and space. Time, obviously the time of the arrest is indicated in one of these columns. So it's a really fascinating data set. Also be aware of the information, the metadata of the data. When was it last updated? August 7th, 2020. And the refresh rate says it's weekly. This tells me that they're behind. I was actually hoping to have an updated data set, but at the very least, it's this month. So it's pretty recent that it's been updated. Okay, so now that we know what data we're dealing with, let's think about how we're going to acquire this data. So Socrata, the platform that this data resides on, has an API, application programming interface. For those of you who don't know what an API is, don't worry too much about it. Just know that whenever you see a data provider and they have an API, think of it as they have a way for you to programmatically access this data. So an API is an endpoint to the data that they have. So many agencies have data in huge databases. And what they do is they suck the data from the database and provide it to the public. An API allows you to dictate how you want to suck that data from their database and grab it for your own purposes. So we're actually going to use the API endpoint for LA's data portal. Right? And to access the data, since we're using Python, we're going to use a library. We used a couple of libraries yesterday, pandas, you know, for visualization, Plotly, Altair, and other things. In order to access data through using Python from a Socrata platform, there's a beautiful library called sodapy. As many Python libraries, it's available on GitHub. It's open sourced. And you can actually look at the source code of the library itself. The sodapy library documentation tells you how to install it. The library has already been installed on our Jupyter Hub, but all the instructions about how to install the libraries that we're using are usually in the documentation. All right, so how are we going to access this data set? The notebook will guide us through this, but before we actually type any code, let me go back to the data set so that we have a real good understanding of how you would go about this if you were looking at a different data set. So one of the things, if we go back to the actual landing page of the data, so arrest data 2020 present, On the top right of the Socrata platform, you will see different ways to interact with this data. One of them is to export the data. So you can just export it as a CSV. We learned how to handle CSV files yesterday. So that's great. You can download it, and then you have it locally, and then you can work with it. You can open it in Excel. The two other options here are KML and shapefiles. KML is keyhole markup language. This is for Google Earth. So this will open in Google Earth, and you can visualize this in 3D space. A shapefile is a GIS file for Esri products. So like ArcGIS, or even QGIS, the open source GIS desktop application. So this is all spatial data formats. But they have another button for API. And this is what we're going to be using today because we're data scientists and we love Python. The API has an endpoint. See the endpoint? It's a URL, which means that if I were to copy this URL and plug it in to my browser, it's going to just give me all the data. And I can see the data within my browser. This is all in JSON, JavaScript object notation format. And this is humongous. This is 40,000 or so records. But we can interact with it through Python in different ways. And one of the cool things here is that there's a link for documentation, API docs. If I click on that, it takes me to a very specific page for this data set. You see the dataset ID up here in the URL, so you know that this content is specifically for this data. There's sample code here as well. There's information about what they call API tokens. So if you wanted a robust connection, you have to apply for a key. Otherwise, the information is free, but you might get throttled, which means if you use it too much, they might throttle your usage. So if you're going to do this for a big project, I recommend signing up for an app token. There's a list of all the fields in the data. I'll get back to this in a second. And then they have code snippets. I always love this. Whenever a documentation has examples, this is what I actually gravitate to as a practitioner. I admit I don't read instructions very well. I just want to get down and dirty. So the code snippets has a tab for Python and pandas. And here, there's a starter code of how to start interacting with this data. Import pandas, we're familiar with that now. Here's the syntax to get sodapy running. From sodapy, import Socrata. And then in order to get this data set, all you have to do is copy and paste this chunk of code to get started. It even puts it in a data frame. The last part of this code says, put it in a pandas data frame. And we spent all day yesterday with data frames. So this format should now look familiar to us. All right, so a question to you all. What is the difference between exporting the data and using the API? So I'll pause here and make sure everybody's kind of caught up. And also, if you could chime in the chat, like, what do you think the pros and cons? You saw those two options. You can either export it or you can use it as an API. So let's hear from you. Why would you use an export? Why would you use the API? What are some of the advantages? Updatability and not sitting on your computer. Yes, Gigi, excellent. And exporting the data doesn't update while on the computer. More streamlined to call the API. Also import CSV into code. Okay, no, those are great. So let me ask you a flip question. Why would you not want to use the API? Data throttling, exactly. Program could indeed be faster without the API. That's an extra connection you need if you're using the API. What if the API gets taken down? I love that. It is so true. You then become dependent on that connection that could go down. The API's change affects your code. You guys all got this. The API is great because once you have your script written, if you run the script tomorrow, and if the data gets updated tomorrow, then your script the results will look different tomorrow without you having to alter any of your code. That's the real advantage of using an API, is that depending on the frequency of updates, it can become a real-time kind of live script that you have running. So if you have something, if this was weather or something, and if you run it tomorrow, you'll have different results because you're communicating directly with the source of the data. Why not to use it? All those reasons are valid. The API endpoint might end, it might change, and then your code breaks. This happens all the time. So when you're reliant on an API, it doesn't have to be like a data API. If you're reliant on like Mapbox or Google Maps API, which I've used a lot, and then they upgrade their API, then your code will stop working. Lots of pros and cons. So when you use data from an outside resource, choose wisely. All right. And thanks all for all this wonderful feedback. All right. Let's get started. And again, with a Python project, the first thing you need to think about is what libraries are you going to use. We covered many libraries yesterday, and I'm going to kind of tell you which ones are relevant for what we're doing for this particular project. We're going to use pandas, so this allows us to read data. We're going to use Plotly Express, which allows us to chart data and do a lot of exploratory, quick bar charts and charting of scatter plots and things like that. I love Plotly simply because it's simple. Matplotlib and some of the other plotting libraries are a little harder syntactically, but maybe more powerful. Plotly is quick and easy. I want to know my data. I want a bar chart. I want it to be interactive. So it's a great starter kind of a charter library. And sodapy so that we can acquire the Socrata data. All right, so we're at our first coding cell. If you've been following linearly this way, then you should be down here. And these are the three libraries, and this is a syntax import, the three libraries. Again, highlight the cell, do a shift enter. You should see the number 1 here. The number in these square brackets is not, it's going to be different for all of us because it's not consistent. In other words, if I run this cell again, the number, see I just hit shift enter again, is 2. So this indicates the order by which this cell was run in that notebook. While the notebook is structured linearly, sequentially, you can run things out of sequence if you want to. It's not recommended, but you can. And that could produce results that are different when I run it than you run it because we ran things differently. For the most part, notebooks are sequential. So you want to run it from top to bottom. But then just to let you know that that's what this number indicates. Okay. Next, we're going to acquire the Socrata client. And I kind of covered how we're going to do that. There's the code that we can copy and paste. This is a subset of that code on the page that I just showed you on the Socrata endpoint. And this is, I just copied and pasted this. But let's understand this. The first line of code here indicates that we're creating a client for the data connection. So here it says, I want to connect to the LA data portal. And next, it says, I want to put all the results from this data set. And this is the ID of the data set for arrests in 2020 in LA. The default documentation limits has a limit attribute for 2000. And then we're going to put this in a data frame. So a pandas data frame, and this is the syntax for it. We're going to put the results into the pandas data frame. I end this with something that is new, sample, df sample, and a number 2 in it. So I'm going to run this, and you should see a result similar to what we have here. Sample, as opposed to head or tail, I love this. It randomly grabs any number you put here. 2, I put 2. You can put 5, 50. It'll grab 2 random rows. So actually, you will have different results down here. If I run this again, I'm going to have a different result set as well. So it's just kind of a good way, if you don't necessarily need to see the first 5 and the last 5, to just randomly check your data. So if you look at the data, okay, it looks good. We have this particular random set got data for May. But what if we wanted to be more specific? Working with 40,000 records is a lot. So what if we want to filter our data to something like, hey, what about all arrests in, actually that's a typo, it should be July. I can actually change that right here. Because August, it's only been updated till the 7th. So we're going to get data for July 2020. How do you do that? There's another argument that we can pass when we get the results from the client, from Socrata, with a where statement. If any of you are familiar with SQL, sodapy and Socrata is integrated with SQL, so you can query the data with SQL commands. So the where statement allows you to put a where statement in the code. If you go back to the documentation, if I can find it, hold on a second, I can't find it, so I'll relaunch it. Okay. Going back to the documentation, you remember the fields that it outputs here. If I were to expand on any one of these, like arrest date, for example, it tells me that it's a date timestamp. And then it gives you like how to query this data, examples of how to query this data. I can go to the query options and go to, it says the query functions for this data type. So this is a timestamp data type. And these are all the operations that you can make to filter the data by time. So you can say, I want time that is greater than May, or time date that is less than May, which will give you time before. Equal to will give you all the data for that particular date. And there's an example of how to structure your query for that. So not to get into too much of the weeds in here, but just to know that the where statement here is super powerful. This data set has 40,000 records. There are other data sets on the portal that has millions of records. You definitely don't want to bring that into a Jupyter Notebook. So for those, you definitely want to think about how you're going to filter the data prior to bringing it in. All right, so now that we have a where statement in here, look at the where statement. It says I want data between July 1st and July 31st. And I have a random sample of 5 outputs here. And I just want to double check. Here's July 28, July 27, July 9, July 21. So that looks pretty good, doesn't it? And it looks like we've brought in all the fields. Okay. Let me pause here, make sure everybody catches up. Are there any questions so far? Is there something I need to address? Going too fast? I don't see any votes for too fast or too slow. Okay. All good, no questions, okay. Just eager to move forward, good pace, thank you. All right, so now let's move forward. Now we have our data. That was step 1, that's a big step 1. even for me to prepare for this workshop, I went through multiple data sets so that I could do the types of analysis that I can. So finding the right data set is paramount for any data project. So we have our data, very happy with it. And now let's do some exploration. So a lot of the stuff that Ben went over, we're going to try to apply it with this data set. So let's try to understand, let's try to feel this data. What can it do for us? So first of all, something very simple. The data frame is, the variable for it is df, and you can do a lot of commands on it, df.shape. This just tells you how many rows and columns. So we have 4,587 arrest records and 25 columns. What fields do we have? What columns are there? I'm going to do a .info on this, and these are the 25 columns that we have. And these are exactly the same as was provided in the documentation. Some of the things that we'll be using today, Rpd Id is the unique identifier. So we know that there is a identifier for every arrest. We're going to be looking at arrest date. So this is the single date. Although it's a timestamp, it is separated with time. So date does not have, all the dates are midnight actually, because it has a separate time field that says exactly when the time arrest occurred. There's interesting like demographic information about the arrestee. So we have the age, the gender, and descent is race. So Hispanic, Black, white, Asian, and so forth. We're going to be using, I looked at this data. I like this particular field, group description. The column name is not indicative of what it is. It's really the charge, the name of the charge for the arrest. And we'll have a look at this later. Oh, yes, of course, the latitude and the longitude for mapping this data. Okay, moving forward. Now we're going to use one of my favorite libraries, Plotly Express. And there's documentations about how to build a bar chart here. So bar charts, so this is the Plotly landing page for documentation. There's all the references about how to, and sample code. If you type this into Jupyter Notebook, you will get this kind of thing. Again, as a practitioner, I'm always looking for sample code. You know, modifying it in a way that fits my approach, my inquiry. So lots of resources here, lots of examples, and we're going to go over some of these. Okay, so let's start with a very simple bar chart. And this is a syntax for PX, right? Plotly Express, PX. And a bar chart, dot bar. We can say dot scatter, dot, and we're going to do a couple of different ones here. So we're going to start with dot bar. The next attribute here within the parentheses is df. That's our data frame. So if you named your data frame something else, this would be different. And then at minimal, you have to have something for an x so that we can plot this data. I don't have a y, so what is this going to do? If I run this, it's going to default to having the count of records in the y-axis. So now x was defined by us. It's the arrest date. So you can see a bar for every distinct arrest date. This is great. So this is the distribution of arrests over time in LA, according to the LAPD. So we see spikes, Independence Day, maybe over the weekends and things like that. But let's dig in a little bit further. And what if we wanted to see a multi-dimensional aspect of this data, not just count per day? So what about distribution of charge types by day? So how would you approach this? First, I want to start to interrogate this data a little bit. We're going to use the unique method here to find out distinct values for particular fields in the data. So we know what fields exist in the data, but I want to know how many distinct, for example, dates there are. And it tells me what I thought it would tell me. There's a date for every single day of July, because that's what we queried for. July 1st, 2nd, 3rd, 4th, 5, all the way to 31st. So that's good. Now we're going to use the group description field, which is the charge type. And following the same logic, I want to know how many distinct values there are and what they are. So this is starting to make sense and is what we expect from this data. We want to know what types of crime is occurring in our city and where. So now we have an idea of how the LAPD classifies their data. We have robbery, assault, narcotics, homicide, vehicle theft, so forth, burglary, drunkenness, and so forth. So this is how we start to interrogate this information. Next, we want to have a count. So we know the distinct values, and obviously the next thing is I want to know, well, how many per count? So how many arrests per day? We did the bar chart for it, but I want a table of results. So again, our data frame here, and we're going to group this data by arrest date. And then we're going to tack on a count. So what this results in is it provides for every date. So we grouped it. So now every row is a group summary for that date. And then we have every field up here in the as columns, and it gives me a count for all the fields that have values in that column. Report ID is the ID, so we know for sure that that's not going to have any null values. There's 121 report IDs arrests on July 1st. You would think there'd be 121s all across, but we have some that are less. And this is because there are records that don't have a description, a charge description there. And that's kind of what that indicates. Okay, so this tells you also at a glance which fields have null values, if that makes sense. Okay. Let's see, why are there no quotation marks in arrest, but there are in, yes, so that's a notation. So the question is, why are there quotation marks in some of these arguments? So for example, here, we don't have quotation marks around this argument, whereas here, it's in quotation marks. So this statement here is changed with a dot. So df dot, and then the field name, and then you can assign an argument after that. This can also be written out with the quotations in this format. And this results in the same thing. So in other words, it's actually the same thing. It's just a different syntax. So you can either do a df and a square brackets to indicate what field you're looking at, of which case you do need the single quotes, or you can use the dot notation in which you don't need the square brackets or the single quotes. It's just a difference in how you access a particular element from within the data frame. All right, so good question. Moving forward, we did the group by date. And okay, so here's a little exercise for you. Show me how many arrests per charge. So we did previously per date. Now I want you to type in the cell how you would do it per charge. Charge being the, what is it? Group description, is that the field? Yeah, group, oh, yeah. GRP underscore description is the charge field. So go ahead and type in the Python code to get the count per charge in our data set. Okay. And in the meantime, if there are any other questions, you can also post it on the chat room. Okay. This is fun, isn't it? All right. So since we know that this produces count by a field, I'm going to copy that and paste it here. So, and all we need to do is change this to the right field. Okay. There we go. Thank you. Someone typed in the correct answer in there. Exactly. So this can be anything. So if I ask you, how would you get the count by race or by gender? You could give me the answer pretty quickly, I'm sure. So this gives us a count by charge. So now we can see charge counts, the distribution of that. Okay. We're going to take this a step further because we want to know how many of each charge type per day. So then we're going to group multiple fields instead of just one at a time. So in this case, we want to do the same group by, but instead of feeding it one field, I know Ben covered this as well yesterday, we're going to feed it a list of 2 fields. The order is very important. The first one is the first grouping, and the second one is a grouping within the first grouping. Okay, so it's kind of like nested grouping. Then we're going to spit out a count. I've added a field after the count so that we minimize the output to just giving me the results in one field. And this is just for keeping everything kind of simple and clean. If I look at the results here, I hope this makes sense. And I outputted the first 50 rows, head 50, just to have a look at this data. And on the left column here, we have the first date, July 1st. And then we have, in order here of the charges, the number of charges on July 1st for that charge. This is pretty powerful. And then we scroll down, we have July 2nd, how many for that charge, July 3rd, and so forth. So now we have a double grouped summary of our information here. Notice, however, that the results, this is called a hierarchical index. So we have kind of a multi-leveled data frame here because we grouped multiple fields. If we want to use Plotly Express, we have to kind of flatten this table. So the next kind of code is to flatten this table so that it's not multi-indexed anymore, but it has a single index. So in other words, we reset the index on our result from the previous slide, and we flatten it. And I'm going to call this the df_flat data frame. The results should now look like this. Now we have kind of a single tiered data frame. We have the arrest date, group description, and a count. Okay. Now we can map and chart this data. So now we'll make a bar chart. Notice here that it's no longer df. We're using our kind of summarize and data set called df_flat. On the x-axis, it's the same arrest date. On the y-axis, we're going to have the count for our summarized data. Now, if I launch this, you will see almost an identical chart as before, except we have these weird lines across each one of these bars. Okay, what are those lines? I'll go to the next slide and kind of do a big reveal here. But this is a stacked bar chart, actually. if we add a new argument here for color, and we add a field for how we want to color this data. So we want to color it by the group description, by the charge. And now this bar chart looks entirely different. It's color-coded by charge type. It even provides us with a legend here. And the legend is interactive. You can actually double-click on any one of these legend attributes and kind of see individual charges over time. Okay. So this is kind of my initial foray into trying to understand this data that we've downloaded from Socrata, from the LA Data Portal, and just seeing this data visually does a lot to my understanding of the information. So I can see just visually which crime types kind of dominate the data and which ones don't, which ones rise and fall over time and so forth. Okay. All right. So now we go into subsetting our data. Are there any questions so far? Just make sure. Okay. Labels in the x-axis are not consistent. The x-axis can actually be defined in the labels. I think there's other arguments. If you look at the documentation for .bar, Plotly Express, there's ways to kind of manipulate the axis. I'd probably look into that. The default state is always hit and miss at times. So I think there's ways to manipulate how they're displayed. Okay. All right. All right. Let's move on to what I love the most, which is mapping. All right. So we're going into subsetting our data. And I'll explain why this is important. Let's go back to our original data set, not df flat, but df. And we look at df.info again. We remember that it has 4,500 rows, 25 columns. What I want to do is create a subset of this data. Just for clarity and for simplicity, we're going to only grab the following fields: arrest date, age, race, charge, and latitude and longitude. So what we're going to do is we're going to copy the current data frame. So here's the current data frame. These are the fields, the list of fields that I want. And then I'm going to copy this into a new data frame. So there's a syntax for creating a subset of the data. The original data frame, a list of fields that you want, double brackets because there's a bracket outside of the list. And then we want to copy this into a new variable, into a new data field. df mini is what I'm calling it. And this is what it looks like. It's just cleaner, simpler, minimizes everything. And if you have a large data set, it makes things run faster. Okay. Same number of rows, different number of columns. All right. Now we have our lat longs. And we need to convert it to a float, because currently it's in a data type called object, right? So we know our latitude and longitude is not a float. In order to map this data, we have to convert it into a float. So we're gonna run this code specifically for the latitude and convert it to as type float. And I'm just gonna run this so that we can look at the results. Here are our 6 fields. Lat long is in float 64. Very good. Okay. So what happens if we create a scatter plot and placing lat longs in the x and y axis? Okay. So I'm going to do a Plotly Express output. Here is what it looks like on a scatter plot. And does this shape look familiar? For those of you in LA, it certainly does. So this is actually a map. Cartesian coordinates, latitude on the on the Y and longitude on the X. So this is our data already mapped. Unprojected, yes. Thank you, Matt. Ready. But let's actually now look at this in a different environment. We're going to use Mapbox, which is part of the Plotly library, which is really awesome. And instead of scatter, we can feed the same level of information using scatter Mapbox. So lat long, Mapbox style here, and I'm going to run this code. And it provides an interactive Slippy map with all our data points on it using Mapbox, which is a web-based GIS platform. I can zoom in. When I zoom in, the base map changes. There's a lot of detail. I can hover over and get information about this. I'm going to quickly actually move in the sake of time. You can play with scatter Mapbox, but I'm going to skip this next step. You know, I'm just going to run it to see the results of what you can do in Mapbox. Again, you can feed it a color attribute and it colors the data. In this case, this is race. But I'm going to move on to another visualization called Kepler. Okay. All right. So this is kind of the new kid on the block, keplergl. They have, it's created by, like them or not, Uber. Uber is full of data scientists because Uber needs a lot of algorithms to determine optimal paths for drivers. And they use machine learning and data algorithms to optimize paths for their drivers. And they made their kind of mapping dashboard open source, which is kind of amazing. So we're going to use Kepler by Uber for our 3D mapping. And again, when you use a new library, you have to import it. So this is the syntax to import the keplergl library. So we're going to run this. So now it's in our project space. And we're going to create our first default Kepler map. So this is the syntax, according to their documentation, to create a default map. When I run this, it should create a map of San Francisco because this is where they're based. So their default is, hey, this is where we're at, San Francisco. This is much like that Mapbox map that we saw earlier. It's called a Slippy map. You can zoom in, you can zoom out. It's very smooth. And it has buttons that we're going to look at in a second. Now, we're going to go through a series of things, but first we're going to add data to this Kepler map. The syntax to add data, map.add data, and the data is our mini data, the data frame for mini. And we're just going to give that layer a name, a res. When I run add data with data points that have lat long coordinates, Kepler automatically, without even telling it which row is an X or a Y, it automatically figures it out for you. So it detects spatialness in your data if it's there. It makes some determinations and it plots it for you. So if your data is configured in a certain way, it'll automatically map the data onto a Kepler map. Let's look at this in further detail. There's a little toggle here on the top left that allows us to interact with this data. Watch closely. I think it'd be best if you watch me go through this process because it's really amazing. And then maybe you can do it later on your own. What we have here is point data. If I toggle the point data, we can see the different options we have here, like changing the color, which are obvious options. We can toggle the layer on or off, but you can change the point to other things. So for example, something like heat map, I can instantly convert this map into a heat map or a cluster map. So when you zoom in, It displays different clusters. It's very responsive, very quick, but my favorite is the grid. So this is a grid of our data. And when you hover over, it tells you how many arrests are in that grid. What is the size of this grid? The default is written down here. Hope you can see this. The default is a 1 kilometer grid. So every one of these squares indicates there's data in that 1 kilometer grid. The color represents how many there are. Let me change this view so that it makes a little bit more sense. I'm going to change the colors so that it's a diverging color set. So I'm going to go from one color to the other. So we're going to go green to red. And I'm going to reverse the colors. Usually a hot color represents high numbers, and a green-blue color represents lower numbers, cold. So now this map makes a little bit more sense. Now we have LA arrests over time in July, red indicating more values. I can also change its quantiles. So for every bucket, so if I show the legend, for every bucket, there are equal number of cells. I can change this to quant size, which is equal interval. I think this map tells me a lot more about what's going on in LA rather than the quantiles. Equal interval means that there is the green, the lower numbers, it more mirrors the distribution of the data. So now we can really see the hot spots more clearly. There are 3 red spots according to our data. Let's take this further. This can be made into a 3D map. There's a height attribute for this data. I'm going to toggle this on. I'm going to increase the elevation. And I'm going to toggle my map. On the right here, there's a button for 3D map. So now we can see this map in 3 dimensions, which is pretty amazing. So we can identify hotspots of crime in Venice Beach over here, some areas in the Valley and downtown LA. Zoom in, you can zoom out, you can use the shift button to kind of rotate the map. And finally, one last thing I want to do is provide the longitudinal component of this data. One of the tabs here is for filters, and I can add a filter for arrest date. And it instantly gives me a chart here on the bottom, the distribution, as we've seen in our bar charts, of the data over time. But I can then look at this data and navigate this data over time. So we can see how crime happens in our city over time. So, and you can play this too. So you can keep this running. All right. So that's kind of, you know, from the beginning of trying to identify hotspots in LA over time, I think we have successfully achieved that. I'm looking at some of the questions. How do you angle the map again? Shift and click, and you can move this map kind of in 3-dimensional space. Make sure that you are in 3D mode, which is enabled by this button on the top right. Yeah. Ryan, that where arrests happen is as much as the presence of police. That is a very true observation. If we look at crime and we start doing predictive policing, we run into all kinds of ethical, political problems, and that's a whole different ball game. So this is, you know, information that's valuable, dangerous, politically charged. So as urban planners, we have to use this information wisely. Okay, I'm going to answer a few of these questions maybe after the workshop. I just wanted to show you one last thing before I hand it over to Ben, which is how to save this data. So again, Kepler provides a very easy way to save the data. So I have save to HTML as the argument. If I run this cell, it should produce an HTML file in your directory. So oh, here it is, LARS, seconds ago, and I can click on it. And what's great about the Kepler library is that it saves the state, the last state of which you edited this data. I'm not sure why the base map isn't showing up, but this is how I left it. And this is how it is now saved. And you can publish this as an HTML file on a website. All right, so that was a lot. I hope that was informative about a start to end of a kind of case study. Again, in the interest of time, I will look at all these questions when I'm moderating. I will answer them as best as I can. Ben and I will be here after the workshop to answer any questions that you have, but I wanted to hand it over to Ben to look at some machine learning stuff. So again, I'll answer questions as we go along. So I'm going to stop my share. And Ben, hand it over to you.
Thanks, Yoh. That's very fascinating stuff. It's really fun to see that. I'll share my screen now and kind of carry off where Yoh was. And I'll just adjust my...
myself. Ben, are you there?
Yeah, can you hear me?
I don't know if I can hear you. Oh, sorry. Yes, I can. My bad. Go on.
Good. All right, so if you've been following along with Yoh on the Jupyter Hub or on the Binder site, I think it's a good idea for the moment to close down this particular notebook that he was working with just to clear up the memory that it requires to use. Rather than just closing down your browser, it's useful if you go up to the file menu and explicitly say close and halt. If you close down your browser tab, the notebook will continue running on the Jupyter Hub in the background. If you've already closed down your browser tab, you can also come up to running to shut it down. It might show up in your running tab, or you can explicitly just open up the file again by clicking on the name. So the first thing that I'm going to talk about is the next one, 05-linear-regression. So I invite you to open that one up. We're definitely going to be kind of switching gears a little bit here. So this is a new topic. I'll be talking about machine learning. Machine learning is another very hot topic. It's not the same as data science, but machine learning is definitely tied very close together with people who are doing data science. Kind of as some introductory comments, what is machine learning? So machine learning itself is a subset of artificial intelligence, but it's not necessarily the same thing. We aren't actually trying to come up with intelligent machines. Machine learning is a way to try and improve the performance of a machine in making predictions. You say that the machine learns and that you're training the machine. Really, the training part of it is that you're developing the capability for the machine to make predictions based on the data that you give to it. There are a number of different ways you can break down the field of machine learning. One is to supervised and unsupervised learning. So in the case that I was talking about yesterday, for those who were attending, I was talking about the iris data set. So with the iris data set, you have measurements of the petal length and petal width and the sepal length and sepal width for different species of flowers. And we had definite label values of the species for given measurements in the data frame that we were looking at. So if we try and feed in a new measurement, say, to the machine of a new set of measurements for each of those 4 parameters, but we don't feed in the species, we can ask the machine, we can feed in a model to the machine and try and get the machine to recognize which measurements correspond with which species. And in the process of training the machine, the training means that we give data to the machine and the machine improves its performance at some given task, which in this case would be identifying the species based on the measurements. And we evaluate it by some performance measure. So I'll get a little bit more to the performance measures later. But that's a basic idea of what I mean by machine learning. I'm going to dive right into an example with Python. I'm sure probably almost all of you have done this before with linear regression. We're going to first look at a very simple case. So simply trying to fit a line to a given set of data is a way to learn what the relationship is between 2 different variables that you're given. So if you've done this with Excel, you might try and come up with a line that has the best fit. Finding the best fit, you could even do this yourself. If you look at a linear relationship between 2 different variables based on different data points that you're given, that would be like human learning, where you're the person who's doing the learning and you're trying to learn the relationship between the 2 different variables that you're plotting. With machine learning, you feed the data into the computer and you tell it that you want to try and establish what the linear relationship is between the 2 variables. And then the computer, based on looking at the data points, will try and figure out what the optimum slope and intercept is for the line. And it tries to do that by reducing the cost function. And in this case, it tries to minimize the least squared errors that it gets between the line that it has and the data points where you have specific values for the line. I'll show that in just a bit, but first, the specific library that we're going to be looking at first is Scikit-Learn. So Scikit-Learn, I've included a link to the web page. This is a very good library to start working with if you're interested in machine learning. So it's intended to be very simple and efficient tools for predictive data analysis. It's accessible to anyone, it's open source. It's built on the SciPy ecosystem of libraries that I talked about yesterday. So it's built on top of NumPy, SciPy, and Matplotlib. And it has excellent documentation. So actually some of the examples that I'll be showing you are drawn from the documentation that are here on these pages. On the introductory page, you can see a variety of different machine learning algorithms. Linear regression is included under regression, where you're trying to predict a continuous valued attribute that's associated with an object. Something like identifying the species for our iris dataset measurements would be clustering, where we have some data points and we want to try and identify the different categories of species with a specific set of variables. Clustering would be if you don't know what the species is, but you expect that there are a certain number of kind of common representative samples, and you want to identify which objects seem similar to each other. In our case, where we do have the species labeled, we look more at classification, where you want to identify a particular class, in this case, the species, that are associated with particular measurements. It has additional pages that talk about selecting model, pre-processing the data, trying to reduce the dimensionality. So if you have a large number of variables, for example, the data frame that Yoh was showing had a lot of columns. Some of those columns might be related to each other. They might be dependent on each other. Dimensionality reduction is a good way to try and reduce the number of variables that you're dealing with. and it can make it easier and faster to train the particular model that you're trying to use. So I highly recommend checking out the Scikit-Learn page. I'll come back here to the notebook. And the first thing I'm going to do, I'm just going to interact with this right inside the notebook rather than in a presentation mode. And I'm going to step through this. You're welcome to step through it with me. I won't be typing in any commands here. All the commands that I'm going to be showing you today are just already written into the cells. So when I hit Shift and Enter to run the cell, this imports the libraries. NumPy, pandas, and Matplotlib are from the SciPy ecosystem of libraries. And then sklearn is the Scikit-Learn library. So there, if you look at the documentation, there are a variety of different classes in the library that you can interact with a variety of different methods and kind of some available attributes that you can utilize when you're trying to do machine learning. You know, so we're taking a simple example where we just want to come up with the best fit line. And we're looking at the case of linear regression. And with linear regression, typical metrics that you look at when you're trying to come up with the best fit line, there's the mean squared error, which tells you the difference in the values between the data points and the theoretical line that you've determined from the data. And there's the R-squared value. So the R-squared value, you want to be close to 1. Mean squared error, you want to be as low as possible. So I'm just going to use kind of a randomly generated data set to start. This first command, NP is our NumPy library, an A range with 50. This just generates an array of data that has 50 points. This, say, is our the X variable that we're going to establish. And then we're going to establish a Y variable as well, which has a linear relationship with X. To introduce some randomness, so I don't just want to plot a pure line, because that wouldn't be very interesting from trying to develop a machine learning algorithm. I'm going to use a normal distribution of numbers. This next one, this shows you that I can generate an array of random numbers. The specific syntax is that the first parameter is the mean of the random variables that are generated, the standard deviation, and then the number of elements that are generated. So up here I have an array of 50 X values. I want to generate a linear relationship with Y that has some randomness associated with it too. So I'm going to say that I have a linear relationship where Y is equal to 5 plus a half times X. And then there's going to be some randomness with the data that we generated as well. It has to have 50 points because there are 50 X values. It has 0 mean and 5 for a standard deviation. So when I plot this, you can definitely see the linear relationship, but there's a lot of variability to the deviation in Y about what that linear relationship is. So this will help us get some sense of how the machine is going to learn the line that's associated with this. One technicality when you interact with a linear regression object from the library, the linear regression object will expect to get a 2D array of values. And that's because, you know, often in machine learning, you can be dealing with many different parameters, not just one. So linear regression can be applied when you have multiple variables and you're trying to learn a linear relationship that's based on all of the different values, just in a linear way, with one specific target value, or actually with multiple. So this line here is just so that I can convert it. LinDF now is specifically like a data frame, but it only has one column. It has one column with all the X values that I've generated. And then this is the part that's where the machine learns what the relationship is. So this linear regression with the parentheses instantiates the linear regression object. And to that object, this is a common thing that we'll see you call a fit method. So the fit method is a way of telling the object to run whatever underlying analyses this needs to do to try and establish, in this case, the linear model, which relates our x values, which are our features, with the target value, which is our y values. And to this, this process runs extremely quickly, actually. You know, almost instantaneously. It's not a very difficult data set. And when it runs, it returns kind of the results of the analysis that it finds. So with the just simple linear regression, the coefficient that it returns, you know, since it can be, since linear regression can occur for multiple different variables, it returns a list of values. In this case, we only have one x column, so we only have one coefficient. This is the slope. So you see it hasn't found the slope of exactly half, but it's relatively close. And it also will allow you to see what the intercept is that it's determined as the relationship. So in this case, the relation, our definition was that interesting. Well, so the relationship was that y is equal to 5. So the intercept it's found is around 2. But let's plot the results. So what I'm going to say is I'm going to plot what the values are that it's learned. There's the intercept plus the linear coefficient that it found times our values of x. So if we plot these, this is the Matplotlib function for plotting. We have our initial x and y, which we're going to plot as red circles. And then we're going to plot, again, our x, but this time look at the values that, that our model is predicting, which are dependent on the intercept and the coefficient, and we're going to plot that as a blue line. So there's the linear relationship that it's found. And we can look at the different errors that it's associated between the data points and the line. We can either call the method, this REG was the returned object from our machine learning algorithm. We can directly call a score and pass in our features. So in this case, it tells us this is like the mean squared error. I'm sorry, the R squared error. The mean squared error, I define that all the way up at the beginning. The mean squared error is a specific function that you can call from the Scikit-Learn metrics that you're looking at. So if we look at the mean squared error, that's around 21. If you take the square root of that to get the standard deviation, you know, that's around between 4 and 5. So that's kind of like the standard deviation that we gave to our data points. And the R squared score simply returns the same thing that as the score for our particular machine learning model method. Yes, so for the questions in the chat, yes, your numbers will be different since they're randomly generated. I didn't include a seed for all of us to try and get exactly the same random numbers. So they will look different. As far as how it got the intercept wrong while getting close to the right slope, you know, I didn't actually realize that when I was creating this notebook in the first place. And I think I have to think a little bit about what is going on there. I'm not exactly sure. It may just be that there's enough random distribution here. So when other people were plotting this with different random numbers, did you get something that was close to 2, or did you get something that was a kind of variable around 5? Okay, so someone did get around 5. I think it highlights the fact that there's, you know, the machine isn't going to obviously learn the exact relationship. It's going to learn a linear relationship because we've told it that we want it to learn a linear relationship. But there's a high amount of variability in the data, and to some extent, the machine learning algorithm is going to incorporate that variability into the model that it's trying to learn. So depending on how much variability you have, some of that gets incorporated into the model that it learns. I see someone also got around 6, so that was higher, and I got around 2. I think if I came back up here and tried to execute this again, since it's a random number, it will generate, I'll keep the x's the same. This now I think looks more clearly like it's distributed around 5. So perhaps in this case, if I run these cells again, so now my intercept is around 6.4. You can see if I decrease the amount of variability by changing the standard deviation of the noise, if I change the noise to be just 1, there's a lot less variability here to the randomness and the linear relationship. And likely I'll get something which has values which are closer to the kind of actual values that I use to generate the data. You know, with data sets, the idea isn't that you have kind of pre-made data. You actually want to learn the relationship without knowing what it is beforehand. This is just a convenience for us. And then if I plot the scores, the R-squared score is much closer to 1 with less variability, and the mean squared error is less as well. Really what we want to do is we want to predict new Y values on the basis of the model that we've trained. So when you're doing machine learning, typically you learn the relationship so that you can, I'd say, predict the target values if you're given a set of features and they aren't labeled with anything. So in the case of our iris dataset, the iris dataset has a species that is associated with every record of measurements. The idea is that you would give that data set to a machine learning algorithm, and then it would learn a relationship, and after it's learned whatever particular, you know, model, it wouldn't be a linear model. In our case, it would be some classification algorithm. But with a classification algorithm, it would learn how to identify particular measurements with particular classes of the species. And then the idea is you could go out into field and just pick a kind of a purple iris flower that you see, make the measurements, and then feed those measurements into the model that's been learned from the machine learning algorithm, and it would spit out what class it thinks of species it is that you're looking at. So I've included some basic things here, which I'm gonna skip over at the moment. You know, it's very simple stuff, so you can look at this later. But what I wanna highlight is the basic flow here highlights some of the main processes that occur when using the machine learning algorithms. So some of the flow that you'll see in the subsequent notebooks that I've included. First we have to load the data. We have to somehow get the data into a state where we can feed it into our algorithm. Here, I artificially generated the data, but I had some value for the features, which were, say, our X, and we had the target values of Y. Then the next step is just to choose the model. Here I knew that I wanted to learn a linear relationship, but linear relationships you know, clearly aren't the only relationship that data can have with each other. In this particular case, it was linear regression. You can have much higher order polynomials that you fit to data. And there are a lot of machine learning is dedicated to trying to find really good models which will allow you to identify relationships between variables. After you've chosen the particular model, then you say that you train the model. And you train the model by trying to minimize the cost function. So here we were minimizing the sum of squares error between the observed values and the values that the model was trying to learn. So this is kind of hidden for you in this library underneath the hood. Underneath the hood, well, so with linear regression, you can actually identify an analytical result to give you what it is that minimizes the sum of squares. With other models, it's not that straightforward, and you have to have some machine learning algorithm, and the algorithm determines the process that the machine goes through to try and minimize whatever cost function it is that you say you want it to minimize, and to learn whatever model relationship it is that you determine that you want to use to model the data. So after training the model, then you can test the model. I haven't shown you testing the model on this particular data, but the idea is that you don't want to use the same data that you've used to train the data to give you an estimate on what your uncertainty is in the relationship that you've learned from the data. You typically want to use new data that's not the same as your training data to try and estimate the uncertainty that you have in whatever model it is that you've learned. Typically, the way that this is done is that if you have the given set of data, you split the data, say, into 80% of the data you'll use to train the model, and then you reserve 20% of it, which isn't used to train the model, but is simply used to quantify the uncertainty that you have by seeing how well your model predicts that particular set of test data that you've left out during the training. I'm going to close this notebook then and hop on to the next one. So with our iris data, I talked to, kind of when I went to the Scikit-Learning page, I talked about both clustering and classification. The next notebook that I'm going to open up is called 06-k-means. So I'm going to use the iris data and assume that it isn't identified with any species. I'm just going to assume that all we have is the measurements, and I'm going to use a clustering algorithm called k-means clustering to see what kind of clusters we can identify in the data set that we were looking at yesterday. So clustering is an unsupervised machine learning algorithm. We're going to assume the iris data isn't categorized by species and simply let the machine try and determine if the kind of the clusters that are present without any guidance from the species labels. In this case, I'm going to also import NumPy and Matplotlib. I'm going to import Seaborn and Plotly and Pandas. Those are different plotting libraries. Ipi Widgets is going to allow us to make some interactive plots. The important ones from the machine learning standpoint are these. So for a clustering algorithm, we still use this Scikit-Learn library. I'm going to import the k-means class, and I'm going to import datasets. So actually, Scikit-Learn already makes available the iris dataset. It's so commonly used that the iris dataset is available simply through the Scikit-Learn library. There's a question, what is the minimum number of data points required? I think purely from a practical standpoint, you know, you can try and train your algorithm on any number of data points. The thing about having not a whole lot of data is that you'll have a large amount of quantifiable uncertainty in the model that you produce. and you're likely not to generalize very well to data that you haven't seen before. So I'm going to import the libraries. Datasets.load_iris will get the dataset for us. This will be in a NumPy array format. So I'll import this. The iris.data will allow us to get the data from this data set. This first colon before the comma tells us that we want to look at all of the rows, which are all of the records of measurements. Actually, let me just show you what the data is. So iris.data is the entire NumPy array of data. It's a list of lists. So it's an array of lists. So the first element is the first record of what's being measured. The target values are included in iris.target, and iris.target is a numerical way to classify the values. So inside of this iris object is also included, which species correspond to these numerical values. I don't think I show that at the moment, but we might be, as I was showing this later. What this first one does is it takes all of the lists, and it takes only those columns from element 2 to the end. So remember, Python is indexed from 0. This is 0, 1, 2, and 3. This gets the second and third columns. So I'm going to plot this with Seaborn so that you can see what it is that we're looking at. In this case, it happens to be the petal length and the petal width, although that's not explicitly stated. The X that I've just defined, the X-axis is identified with this X array that we've defined. It takes all of the records and looks at the first column. The Y is all of the records in the second column. So we're plotting one value against one variable against another variable. We're coloring them with their target value, which is the Y. Y is our target. And then this just defines the color map. So it tells you, you can visually see the different clusters in the actual data set when we're using the targets here to show us how the data is actually clustered. Although we aren't going to use the labels in our clustering algorithm. So those that are labeled as 0 are down in this corner. There's another category of species which are kind of more towards the center, and another category in the upper right. K-means is just as easy to run as linear regression. So the first thing that you do is you simply instantiate the object by calling your particular model. In this case, this is K-means. And then we pass in the number of clusters that we want to try and identify in the data. So with this particular K-means, we explicitly say the number of clusters that we want to try and identify. When I do that, calling this instantiates the object, assigns it to the K-means variable, and then to run the machine learning algorithm, we call the fit method. And we don't have a target value. We're just trying to do clustering. So we call fit on X, which has the 2 columns of data. And then once that runs, so it's not a heavy data set, it ran quickly. K-means now has, you can identify the parameters that it's learned from the data by looking at the particular parameters in this object, one of which is labels. So the labels is just for each record that's in the this X array. It tells us it identified all of these as one cluster. It identified all of these as a second cluster, kind of with the exception of those 2 points. And then it identified all of these with the exception of this one, with, actually a couple of them as its own kind of cluster. So now what I'm going to plot is I'm going to plot, this is our data set, the first column, the second column of the data set, and I'm going to color them not by their species labels, but by the labels that was learned from the k-means algorithm. And you can see it is very similar. It got the cluster down here perfectly, you know, but there is overlap. There's no overlap here, I should say. There's no overlap between these two different colors, whereas in the actual data set, you can see there's some interpenetration in this particular parameter space, which is why the clustering algorithm didn't get this kind of perfectly right. It doesn't just have to be for 3 clusters. You know, if you're just being presented with data for the first time, you might not know how many clusters it is that you want to try and identify. I'm not going to go through that same process with, you know, multiple times and try and do for different clusters, but I'm going to make it a little more interactive with a Python library called Ipi Widgets. So this is a library that is one of my favorite libraries. I love to interact with it because it gives you interactive visualizations. Here I've defined the basic functionality that we already ran in our previous cells. So I'm going to call the k-means, I'm going to instantiate the object for a different number of cluster depending on how this function gets called. So calling def k-means iris, this is the name of the function that we're defining. This is a parameter that we pass into the function. Then there's a colon, and these are the 3 commands that get executed when you execute the function. So we establish the object, we call the fit to establish what the labels are, and then we're going to generate a plot, and we're going to color the points by the label that's been established by the algorithm. And then Ipi Widgets.interact is the way to, I'll execute this and you can see. So this particular library, when we call it, we pass in the name of the function that we want to interact with. And then another parameter that we pass into the function is the variable name for the parameter that has to be passed into the function. And then here I'm passing it a tuple of integers. And what that does, it tells this particular interact method to give us a slider. And this slider will vary between 1 and 20. And it will execute the function depending on what the value of our slider is. So what we started at was 3. This is our 3. And I'm just going to press the right and left arrows on my keyboard. If we look at 2, you know, there's clearly a difference between this and this, although there's one funny point that's right here. We'll look at that in a second. Just looking at 1, you know, this is a rather trivial example where everything is just identified as being in the 1 cluster. So there's a certain arbitrariness to the k-means clustering. It simply identifies the number. It tries to identify the number of clusters that you've told it to identify. And if you go up higher, you know, in this particular one, it can be fun just to see the different clusters it tries to identify. Petal length versus petal width, if you remember from yesterday's exercise looking at the data set, these 2 parameters were one of the cleanest to look at because you had a clear separation in this species down in the bottom. It can also be important, we have more than 2 columns of measurements. So we have a 3rd and a 4th. We can't visualize the data in 4 dimensions, but we can try and visualize it in 3 dimensions. So I'm going to call the Plotly library that Yoh was showing before. This is the same function, essentially, as what was here, except I'm using the Plotly scatter_3D to generate the plot. I now pass in 3 columns from the data, the 0, the 1st, and the 2nd. But essentially, other than that, it's the same. I do redefine X here to be from the 1st column from column index 1 to the end, so that we actually have 3 different columns rather than 2. So this now is going to generate a 3D plot. I may actually have a, let's see. Oh yeah, here we go. So this allows us to see, you can take your cursor on this and drag it. So here's, or rotate it in space. This is the petal length versus petal width. This is kind of that relationship we were looking at before. You can also see a relationship, say here, between 2 other variables in kind of the other 2D, 2 dimensions to look at. So this allows us to, you can also zoom in. You can get a better idea of where, say, some of the problem spots are with the, how the clustering is identifying the data. So what I was talking about before was when you have 2, there, you know, there's a point out here which is clearly not in the second cluster, which it is identifying kind of more with this cluster than with the other cluster up here. So what k-means clustering is trying to do is it establishes 2 different points, and the cost function that it's trying to minimize is the variance of the data points around those 2 points that it's identified. So part of the algorithm is starting with initial points in this particular parameter space for your cluster, and then it moves those data points around to try and minimize the variance of the data that you have about these 2 points that it's identified as being the centroid of the clusters. So I have some additional functionality here which will allow us to see where the center of the clusters are. For the moment, I would say I'm just going to run through this and get to the last graphic, with the exception of one thing. You can access, you know, just like we got the intercept and slope from our linear regression object, here now there's the cluster centers that we can extract from our k-means object. And this tells us the location in our particular parameter space where it's identified the clusters. So I think you can ignore this error for the moment. If you're interested in that error, I can tell you what it is. But here, the final graphic allows us to see the different centroids around which k-means thinks that the clusters are clustering. So with 3, you have this centroid, this one, and this one, which fairly well identify actually the different species. There are 3 species of iris here, and it will do a pretty good job of identifying them. When we look at 2, the reason that the clustering algorithm was showing that kind of outlier of points, you can see is because with 2 you're only allowed to vary 2 different points. There's this centroid and this centroid. And it tries to get to the point where it minimizes the variance. But this particular point out here is closer to the centroid here than it is to this one. You know, it's kind of probably right on the edge where it could, if it was just a little more in the other direction, be identified with this one. So this gives us a sense of what one of the unsupervised algorithms is. I'm going to close this notebook now and go to one that's a supervised algorithm for looking at classification, and that's called Logistic Regression. So I'm going to open up the one that's 07-Logistic Regression. And first, what I'd like you to do is just come up to the cell menu and say Run All. And that will run all of the cells. This is not looking at petal length versus petal width. This is looking at sepal length versus sepal width, which is why the data points look like they're differently distributed. But the data points are, here they're colored, they're colored by the particular species that they're identified with. And then the space behind them is colored on the basis of what the logistic regression algorithm has identified as its kind of the boundaries between where it would predict one species exists versus another. So here, logistic regression comes from the particular function that's used in trying to identify the different classes. If you want to look it up, you can look up the logistic function. The logistic function looks like a sigmoid curve or like an S-shaped curve. So with logistic regression, you try and identify a probability to each of the classes at a point in space. And the logistic regression algorithm will identify the particular class that just has the highest probability at a particular point in space as being this kind of the class that it's going to say is identified with that point. So here, now this is a supervised machine learning algorithm. So it's using the fact that the measurements have actual target values that we know. So in our data set, we have not only measurements, we have the target values, say, that we would later try to predict from the algorithm that we've learned. And we can use that target value to inform what the machine learning algorithm does to try and learn the relationship. It uses a logistic curve to try and determine the probability of a data point belonging to one of the different classes. The flow of this, if you come through it, is very similar to the flow of the notebook that I showed previously, with the exception that I'm just tossing in some different classes. So rather than k-means or linear regression, now I have logistic regression as what I'm calling from the Scikit-Learn library. I still load the iris data set. I look at what the iris data set is. This is how you can get the feature names. So we do now have to identify the particular measurements with particular target values with particular classes. The feature names gives us the names of the features. Target gives us the target values, which are numerical, and then target names gives us the name of the species that are identified with these particular labels. We subset the data. So this initial part is simply getting and kind of massaging the data if we need to. And then you get to something which now hopefully looks familiar. You call the name of the model that you want, which in our case is logistic regression. We assign it to a variable, and then to that variable name we call fit. And fit is the method that runs the algorithm. And we pass in both the feature values and the target value that we're going to use to learn the relationship that's underlying this model. And then these next ones, if you want to work through this is just a way to establish a two-dimensional space that we're going to plot in Matplotlib. And then we've come to something new, which is predict. So in addition to fit, you can call a predict method. And in this case, we're not just learning, well, we're not just trying to make a plot that's, only has a prediction for a few select points. What I've shown you is an entire space that we've colored based on what the prediction of the algorithm is. So to the predict, I pass a NumPy array, which has this two-dimensional grid of values. And for each value on the grid, which is what's ended up plotting here, it uses this model that it's learned to predict what the class is. I assign all of those classes to a variable. And then this is the Matplotlib. These are the Matplotlib commands that allow us to plot this one called color mesh, plots the grid of values, which are XX and YY, depending on what the color is of the class that we predict. And then on top of that, I plot this one, which is a scatter plot. And the scatter plot has just the first column of data plotted versus the second column and colored by what their target value is. So here, the target, you can see where the target values aren't being correctly predicted by the algorithm that's because there's overlap between these data sets. They aren't perfect. They can't be perfectly differentiated by, say, a specific line here. If you come to machine learning algorithms, you can learn very nonlinear boundaries between these different data sets. So some algorithms, as you start to get more complicated, or as you work more particularly with this one, will allow you to learn more complicated relationships between just a simple, say, linear boundary between classes. But this hopefully gives you a sense for, how easy it is to use the Scikit-Learn library to try and learn a model which you can use to make predictions on values that you haven't yet seen. So I've covered supervised learning and unsupervised learning. I can stay and talk more if people want about two additional libraries that I've included here, just because, they're very hot libraries at the moment. TensorFlow and PyTorch are called deep learning libraries. And with deep learning libraries, you can use neural networks. I'll just introduce it to wrap up. But you can work through these later. The general method that I'm showing in these notebooks is very similar to what I was showing in the other algorithms. So there's the first part of it is importing the data, importing the libraries, kind of massaging the data a little bit. In this particular one, I do kind of split the data into a training and a testing portion. Then you simply define the model. So with Scikit-Learn, this was very easy because you just instantiated the object. With neural networks, it's a little more complicated because, well, clearly I don't have time to tell you what a neural network is, but you have to define different layers to the network. But after you define the model, you train the model also by just calling the fit method. You can evaluate it, and then you can look at the loss and you can use it to make predictions. That's the very basic flow that you'll see in a lot of these machine learning algorithms. That's the basic flow, and then you kind of just have to piece in different algorithms, different models, different cost functions, different data sets. But this general idea of the procedure is what people use to use machine learning to draw conclusions and make predictions from data sets. So I'll stop here for the moment and ask if there are any questions. I know I went over it kind of quick. You can run these notebooks just by coming up to the cell menu and saying run all. And that will run them all. You can see the different results that have been generated. In this particular one with TensorFlow, you can see it decreasing the loss as it's learning the model and increasing the accuracy. And you can try and feed in different measurements and get predictions. With PyTorch, it's actually very similar. And I intentionally tried to set it up similarly so that you could see the basic flow.
Maybe we can pause here for a second before maybe you can quickly go over the PyTorch notebook for those who are interested. But given time, we're past 11. Maybe we can pause and get some feedback. If there's things you want to review or ask again, feel free to do so right now.
Yeah, and certainly on Yoh stuff too, if you want to ask. We can trade off too if you had more questions about the Kepler or the GIS visualizations.
I think one of the challenges that Ben and I had to put this workshop together is knowing that all of you come from so many different walks of life on what kind of content to put together for like an intro to data science. So it helps that I'm more of a North Campus person and Ben is a South Campus person. So we can kind of feed off of each other. But yeah, let us know if you have any questions. Once again, these sessions were both recorded. They're going to be transcribed and posted on our Idri YouTube channel. We'll send you an email. Every one of you will get an email with both links to the YouTube videos as well as a poll. I know many of you have done many polls for our workshops before, but we do look at them very carefully. It helps us know how we can improve and how we can cater the content to better suit you. So ultimately, we really want to make these workshops useful to you. So that's what we want to hear. We love the positives, but we look very closely at the negatives. So we'll send out a poll as well as the links to the video.
Mm-hmm. And in particular for this material, I think, you know, it'd be good to know if people have suggestions for how to structure it, or maybe, you know, what topics to include or what might not be necessary. I think that would be helpful.
Right.
TensorFlow and PyTorch do, yes, have convolutional neural networks. So here with, for anyone who's interested, you're welcome to interrupt me if you want to ask questions before you sign off. The basic idea with the neural network is, say with, you would feed in the measurements, you have a variety of different layers here, which are connected together. So the idea is you take a measurement, you apply some operation to it at each of these nodes. This is a fully connected network. So all of the nodes are connected to each of the other nodes in a subsequent layer. And after applying the operations, you know, which can be linear or nonlinear relationships, operations, you finally get to values. Say you want to try and identify three different values at the end. And if these were probabilities, say you would get a probability, three different probabilities which sum up to 1. And you would take the highest probability as the probability which indicates which class you want to identify this particular set of measurements with. So the basic idea behind neural networks is that you take each data point, you propagate the data through the network, and then you identify, this is supervised learning, so you have an actual target value. You identify the error between what the network produces and what the actual value should be. Then you take that error and you propagate back through the network. And you can do this in a mathematical way to try and determine a step that you can make for each of the nodes to try and improve the error based on the error that you're seeing. The idea being that eventually you're going to modify the errors in such a way that you improve the ultimate predictability of the network. So you go forward, you identify the errors, then you go backward and you tweak the operations that each node is doing. You feed in another one, you go back and forth, and you do this however many times you want with the test data that you have. When we come down here, you know, the importing data, I think you're probably very familiar with at this point. The model itself is simply, in this case, it's a sequential sequence of layers. They're dense layers because each node is connected to all the nodes in a subsequent layer. You say how many nodes you want. There are different things in here, but the idea is with the first these are all the successive layers of the network. You feed in one which the input shape just has the number of features, which for the iris data set is 4. In this particular case, the next layer of nodes has 10 nodes, then 8 nodes, and then finally 3. And you want 3 because you have 3 different species that you're trying to identify. And to this model that you've defined, you call a compile method where you specify how you want to try and identify the errors, what metric you want to use to identify the errors, and how you want to change the value of the nodes depending on what the errors are that you've measured. That's what this optimizer is. And then you simply call it with the fit method. So you call this is the feature set, this is the target values. Epochs, the epoch count is the number of passes that you make through the entire data set. So this will go through the entire iris data set 150 times. It'll use 32 data points before it goes back through the network to try and modify the operations that the nodes are going to be doing. And then this callback is just a way for me to store information about the loss and the accuracy that are recorded each time. So what it ultimately does, it starts out, at a higher loss as you, this is the epoch count, so it goes from 0 to 150. As you run this multiple times, it decreases the loss, it improves the accuracy of its predictions. You'll see a different value for this, when you run it too, because there's some randomness that's as to what the initial values are when it starts. So there's a question, how did I pick 8 for the second layer? There's at the moment, I don't know if there is a very determined way to be able to identify what the optimum number of nodes is for a particular layer of the network. To some extent, this is arbitrary. To some extent, you train a network with different values of this to see what gives you the best results. So changing one parameter in your algorithm and trying to vary it to see which model gives you the best results, this would be called a hyperparameter. So hyperparameters are parameters that are inside of your machine learning algorithm, which aren't identified with the ultimate predictive model, but can be varied to vary how the particular model that your algorithm is learning. Let's see. So if, I can go ahead to the PyTorch one. Unless people want to jump in with any questions, again, feel free to do so. With the PyTorch one, so the TensorFlow that I'm showing is actually using another library as well called Keras. With Keras, here. So from TensorFlow import Keras sequential, which is what we use to instantiate the object for our neural network, is taken from Keras, and the dense method is also taken from Keras. So Keras kind of sits on top of TensorFlow and allows you to very easily define what the model is. TensorFlow, you can also modify it on a much lower level, where you try and be, there are a lot more specifics that you can specify. With PyTorch, if you run this one, I'll run this again with run all. The basic idea again is that you import the libraries. In this case, the library is called Torch. We get the data. We split the data. This train test split is actually from the Scikit-Learn library. And this is a very easy way just to split your data kind of in a very good type of splitting way into a part that's reserved for testing and the part that's used for training. For Torch, you have to convert the data into a tensor object. So when you define the model, you define the model as a class. The class has an initialization where you define the layers in your network. In this case, this again has 4 input features. I guess here I defined it with a different number of nodes, but it goes from 4 features to 16 nodes, from 16 to 8, and then from 8 to 3. And then on this, you also have to specify the forward method. So the forward method is what it uses to propagate information from the features forward through the network to the end where you get your classification. RelU is a particular activation function. RelU is also used in the here in TensorFlow, where I said RelU was here, activation. So activation is kind of how it determines different operations that it's going to apply to the data as it's propagated through the network. You apply those to the data from in the first, say from the features to the first layer of nodes. You apply RelU to from the first to the second. And then the Softmax activation, Softmax is used when you want to get a final set of results which all sum to 1. So in this case, it's like your probabilities for the 3 different classes. The output features are 3 and you apply Softmax. So when you look at the values that it's predicting, they're like probabilities for the different classes. And all of the 3 values sum up to 1, so you have a probability of 1 at the end. This simply just prints out what the model is. And then you define how you assess your error. This is for classification, multi-level classification, it's common to use something called cross-entropy loss and to try and optimize it with something called ADAM. This is kind of related to what is defined here. I'm sorry, what is defined here for the optimizer? So you define a criterion for assessing the error, an optimizer for how you're going to use that error to inform updates that you do to the network. And then you execute a loop where you step over the epochs. So the PyTorch I'm showing you here is kind of a little lower level than what you get with Keras. So I'm kind of specifying these more in with the classes and the methods and the specific functions. Here's the forward pass. Here's looking at the criterion for the errors. And then this sequence of commands is how you use the optimizer when you're propagating that error back through the network to update the operations that are executed by the nodes. And then this final part is just about evaluating the mode of evaluating the results that the model has learned, and then you can look at the loss. So the loss here also decreases as you run the machine learning algorithm. PyTorch and TensorFlow is kind of significant overkill for the Iris dataset. These are usually run on very large datasets that have very nonlinear relationships with them. And one thing I haven't really mentioned is that with a lot of the libraries that you use with Scikit-Learn, you get a good idea of, it can help to inform you in some sense with a more conceptual understanding of the relationships that you have in the data. With PyTorch and TensorFlow, with neural networks, you don't really get a ready-made, easier conceptual understanding of what's happening. The information is encoded in the operations that the network has encoded in it. And it's not like you can say, well, you know, petal length increases when petal width increases. that information about the relationships is encoded in the network and it's not easy to abstract. So neural networks can be very good in their predictive capabilities, but not so good if you want to increase your conceptual understanding. In that sense, they're more like a black box. Let's see, so any other questions?
All right, are we ready to wrap up here?
Thanks everyone for joining.
Yeah, thanks everyone.